Okay, I hope things are clear with spectrum, standard spectrum, why you need it, how you do it and where you apply it, etc. If you have any doubts, please ask. If you do not have doubts, I just proceed. Okay. And I have given most of the salient information. If you want to adopt or apply all this information, I suggest you go through some books as well as lecture materials available along with this lecture, so that things will be more clear. And also you can try use this WAFO, you will get a lot of experience how to handle all this spectrum, etc. Earlier I had just highlighted about the necessity of simulating a wave profile from a spectra. This is often referred to as simulation of ocean waves of predefined spectral characteristics. So, if you are having a kind of a facility wherein you can simulate in the lab ocean waves of predefined spectral characteristics, that means you have an excellent control over the wave maker. Okay. And these days several labs worldwide have this kind of facilities, and so there is a lot of work that has been done by using different kinds of spectrum. Now here we will just look at some of the mathematical aspects of this energy contributions or the simulation of waves from a spectrum. So if you look at this picture, forget about the units, but you just look at, for instance, this frequency. Over this frequency, this is the amount of energy that is contributing to the total sea wave at frequency, that particular frequency. This is often referred to as peak frequency. Apart from that, if there are any other frequencies where you are interested in knowing the energy content, that is possible. That is, how do you simulate from a spectra? So here the wave height at that particular frequency which I was mentioning, that is, let me call that as f1 h of f1, that is the frequency at, the wave height at frequency f1. So the wave height or at frequency 1 will be 2 times the spectral density at f1 into delta f. So delta f is the frequency interval, the spectrum will have a constant frequency interval. So that delta f, you have to multiply it 2 times square root of twice the spectral density at that particular point. If it is amplitude, this will not be there, okay. Since we are talking about wave height, you will have this 2 times, okay. And you also try to associate what we are discussing now with the problem which we worked out, wherein we try to obtain the spectral density for different frequencies. For different frequencies we try to obtain. So once the wave heights h1, h2 etc. were given for frequency 1, frequency 2, I think we took about 5 frequencies, right. Then we found out what is the energy content for each frequency, and then and when we found out the total, we obtained the total energy under such a combination of waves. The same exercise only we are doing it here, and the corresponding wave period, that is when we say here what is the wave period at this 1 by wave period is 1 by f1. In fact this can be referred to as t1 or tx. So h and t will constitute a wave height period pair. So that is the simulation of wave profile from a spectrum. But where does the random number comes in? A random number comes in when it is associated with the phase. See, you can, when I have a wave, so if all these waves, a number of waves, if it has the same phase and you superpose, you are not going to get a random wave. When you want to have a random wave, then they have to be superposed, different frequencies etc., and a random number, the phase has to be set as a random. I am sure all of you know what is meant by phase, okay. So that phase is chosen as uniformly distributed from 0 to 2 pi, and this random number can be generated by a random number generator. It is quite straightforward, and this random phase is, for example here it can be defined as, and Rn is the random number, okay. So at any given location, see we are working with the 2 variables, one is x and another is t. Later we will also be working with x, y, z and t. Now at this point we are considering an horizontal axis x at any given point at which the wave profile is decided. So for example, I have a tank and I want to define at this location the variation of the wave elevation. So my wave maker is here, so my desired location is x. At that particular location, now x can be set to even 0, no problem, okay. So then I use this expression at a given point x as a summation of n to capital N. This n to capital N is nothing but the number of frequency components, and it is a summation. That is what I have been telling, that you add all the components. This number of components is up to you. So, the quantity n is the total number of frequency bands of width delta f dividing the whole total energy density in the above figure. I mean, you take the total figure and then you can slice it into number of frequency bands and then you can do the summation. Now, sometimes Fn is chosen randomly within each delta f for more randomness. So, within the delta f itself the frequency, see within delta f is this, within the delta f itself the frequency will be changing, right. That is a very small interval. Within that itself, if you want to have, you can still do that by introducing the randomness within that delta f. So, basically you see that you have wave height which is h wave height of nth component where n is equal to 1, 2, 3, 4 etc. up to n, and then k of n, that is nth component, that is k is 2 pi by L. So, each of this is, when I say h of n and k of n, this is clear, and this is 2 pi L of n, okay. So, that is, this is a pair h of, this is what we are trying to represent in terms of n number of. So, n will be ranging up to n equal to 1 to capital N. Capital N will be total number of components that are going to be superposed. Is that clear? So, that is a very simple way of simulating the time history. So, once you have your the mathematical expression, you can simulate any kind of I mean the wave elevation from any kind of spectrum, and some of the examples we have seen just now, okay. The method outlined earlier requires a given spectrum, maybe Pearson, Moskowitz, Scott or whatever it is, or an actual input wave energy density function. What does that mean? It can be a theoretical spectrum, maybe PM spectrum, or it can be a measured spectrum. For example, you have measured some spectrum of Bay of Bengal and you want to use that spectrum in the lab, you can still do that, the principle is same, you understand. So, you have, see, you can always say that I have already the measured time history from the Bay of Bengal, that is also possible. You can still use this time history to your wave maker and do the work, or if someone gives you only the measured spectrum and not the time history, then you are forced to simulate your time history on your own, for a simple reason you do not have this, okay. So, it can be either the theoretical spectrum or the actually measured spectrum from the ocean. The spectrum curve or the spectral curve is divided into a number of equal divisions. It is not necessary to divide the spectrum equally, it is done only for computational convenience. All these guidelines have been just taken by from the book of Professor Chakrabarty, because it is so clearly explained. So, I do not want to make any changes. So, moreover, if a number of if a sufficient number of components is used, then it will be suffice to use equal increments of delta f. Usually we resort to equal increments of delta f. Our delta f is always constant. Okay. At this point of time I would also like to say that there is what is called as Nyquist frequency, which is 1 by 2 into delta t. Okay. So, or the cutoff frequency beyond which we say that up to the Nyquist frequency at least the 90% of the, if suppose if your cutoff frequency is somewhere here, which is defined by this, and this delta t is what? Delta t is the digital values of the signal taken from the mean line. So, this sampling interval is delta t. You have to be careful in taking this, choosing this delta t. So, we say that the cutoff frequency beyond which within this area at least 90%, 95% of the total energy is already accommodated. You have considered 95%, minimum of 95% of the energy contained. Now, the number of components should at least be 100 to assure randomness. So, if you take just very few number of components and try to do that, it is not going to, you do not have the randomness coming into picture at all. When I say randomness, also try to have this autocorrelation coefficient, how this would look like. I have explained in earlier class. So, it should be at least 100, use of about 200 components duplicate the spectrum accurately. So, the number of components can be around 100. So, that is based on this model. The value of wave height of course will differ for different values of delta f. For different value of delta f small, this method, if delta f is small, this method produces a satisfactory random wave profile. Now, next let us look at this method is widely used method, it is a widely used method in simulating random waves for a given energy spectrum, we have seen already, and it is also called as deterministic spectral amplitude model or method. Since herein the amplitudes of individual wave components in this superposition method are deterministic. So, you can get the amplitude of each of this spectrum. If you consider a particular spectrum, the amplitude can easily be estimated. So, look, just now I had this expression here few minutes back. How do you get at this particular frequency, how do you get the amplitude as a function of spectral density? So, this is quite straightforward, and that is the reason why it is called as a deterministic spectral amplitude model. Only the phases of the individual components are randomly chosen, and thus the method may also be termed as random phase method. So, I will just the last one is, it has been shown by Tucker et al. That this representation of random wave simulation does not satisfy a condition of a Gaussian C unless n is infinity in the limit. What is meant by Gaussian process? As I said, the wave elevation usually follows a Gaussian process, that is, it follows the normal distribution. N eta is minus infinity to plus infinity. Okay. this is the variation. So for this, when you draw the Gaussian distribution, it will be something like this. So your measured points will be, so then you say that it follows a Gaussian distribution. I have mentioned that if eta follows a Gaussian distribution, then wave height would follow Rayleigh distribution. So if you want to have some kind of a condition that you want to simulate waves that follow Gaussian distribution, then you have to be careful, take necessary action, or be careful while using this method. Sometimes you may be interested not to generate a Gaussian distribution, you may be more interested in generating a non-Gaussian distribution. That is, if it can be either the measured spectrum, measured probability of your maybe positively skewed, so this is measured and this is the theoretical Gaussian, or it can be negatively skewed, okay. So this is what is called as non-Gaussian distribution, okay. Now an alternate scheme to represent the sea surface would be in terms of two Fourier components, in terms of two Fourier components. I am sure that all of you have the basic knowledge on Fourier series, I will not go into all those aspects. So now eta of x comma t can be represented as, here you have the summation, something like the Fourier series an, bn amplitudes, and then the other all the other things take care of the phase variation. So in this case an and bn are obtained as independent Gaussian distributed random variables with 0 mean and variance of so much, okay. Variance we have already seen. Thus amplitude and a phase are equivalently replaced by two amplitudes, which are the coefficients of sine and cosine components of the wave profile. So you see that this above equation is a proper representation of a Gaussian sea. So n should be still be large if you want to really simulate a true random sea. This I believe it is also referred to as a random coefficient scheme. So the entire wave elevation is now represented as a function of in the form of two Fourier components, coefficients. Is that clear? So one is the earlier DSA model, and now since the amplitudes and amplitudes are random in the case, this is now called as non-deterministic spectral model, because now since both the amplitude is random in this case, the amplitude is random in this case when you are defining the wave elevation, unlike the earlier method, unlike the DSA model. Now the main difference between DSA and NSA model is the satisfaction of the Gaussian sea. If you use NSA model, you will more or less have a Gaussian process, and anyway you have to use more number of a large number of superposition of large number of components. But in the DSA it is somewhat doubtful, whether you are going to land up with a Gaussian process. By chance you might land up with Gaussian process, but it was Elgar et al. Where he showed that there is no significant difference between the two simulation schemes in many of the wave group statistics. In both cases, whether it is a DSA model or the NSA model, it is always better to use more number of components. When you use the inverse FFT, the number of components you are going to superpose will be n by 2 components. So, where n is the total number of data values, that is total number of data values, I mean. So, if I say eta of I, so I equal to 1 to maybe 4000 something, 1024 or 2048. Normally this is what they do for lab experiments, okay. So then the number of components will be 1024. So I suggest you also Bendit and Pearsall. The title is something like random data. The reference is given, but I suggest that I just make a mention here, Bendit or Pearsall, that gives a lot of information about the basic statistics and how do you treat the random phenomena. Now, having an exposure to the simulation of predefined spectral characteristics using both the DSA model and the NSA model, we now get into what is meant by wave atlas for the Indian Ocean. It is not actually Indian Ocean, it is Indian Ocean plus along the Indian coast. This was published, this is an old atlas, but still it gives us some kind of indication concerning the wave climate. There are so many sophisticated models these days and so much of abundance of information on the wave data. But the reason why I have considered the wave atlas is the way you present the results, the way the results are reported to you on the wave characteristics. So this was published in National Institute of Oceanography, and 19 years of ship observed data was considered, and wave height and wave period presented in the form of Rose diagrams. This is called as either wave Rose diagrams or wind Rose diagrams, or wave height Rose diagrams or wave period Rose diagrams or wind speed Rose diagrams. So wave directions are represented in 10-degree interval, d theta I will say. The Indian coast is divided into 10 grids, and about 29,000 swell data points were compiled for the whole region. So this is the Indian map, wherein the whole area is divided into a number of grids as mentioned earlier, and then a wave height roses, method of representation, percentage frequency of occurrence of each class of wave height in 10 degrees interval as for each month, for every month. So starting from January, February, etc., for each of those grids. For example, if you take this grid, it is available January, February, March, all the 12 months, compiling all the 20 years of data, and it gives the probabilistic description of the wave heights, wave periods coming from different directions at that particular grid. You understood? So the percentage of frequency of calm is given in the center I will come very quickly, we will be seeing the Rose diagrams. Spacing of concentric circles represents occurrence of frequency for occurrence of force. So you will have concentric circles, and you see here the concentric circles represent number 4 as I have indicated here, I mean the frequency of occurrence as 4. Then you see the lines, each line indicates the direction. So you take a particular location, particular grid, so in a particular grid what you have in the center is the percentage of occurrence of the calmness. All other things are given here. So you have a scale with a percentage of occurrence of 4 in terms of 4, and here is the percentage of occurrence of wave height in period meters. So each of these indicates these values indicates how much is what is the percentage of occurrence of wave height ranging between 2.5 meters to 3 meters. All this information can be obtained. Similarly, you have the wave period Rose diagrams, the same procedure is followed, and you have the period in for example here percentage of occurrence and same thing, and you see that this is how the period diagram is presented. So before that there is another aspect, that is scatter diagram. This also is used for a given location, say for the month of January. Data has been acquired, so it may be measured data, it may be measured data. So you will have HS in meters and TP in seconds. So you may have 5, 6, 7, 8 etc., and then here maybe 0.5, 1 meter, 1.5 etc. So here in this maybe you have 10, 25, 30, 40 etc. Okay. So what does this mean? This gives the scatter diagram. This represents the scatter diagram, which gives 25% of the time the wave height is approximately 6 seconds with an associated wave height of 1 meter. Similarly here the most frequently occurring combination is a wave height of 1.5 meters with a wave period of 7 seconds. This kind of information is very useful for the design of structures. In addition, there is also what is called as persistence diagram. So you have to look for how long a storm can last in a particular location. This also is important, this also is being used. Okay, I think I will stop with this, and then we will see in the next class.